design tools, modeling. I guess from my perspective, we're all designers. We all do some sort of analysis. And so, before you start building things, you're going to be thinking about design. You're going to be thinking about how's this product going to behave. And of course, you want to do as much analysis on paper, or what's traditional today is to use more digital computational techniques in trying to understand the design and its behavior, performance, and reliability. So I'm going to talk about the work happening in design tools and modeling. In the center, as a summary, you've been hearing a lot of that in each of the presentations this morning. Design, modeling, and analysis is coming strong. Is coming along very, very strongly in each of those themes. My focus here will be more about what we're doing in the cross-theme projects and some of the challenges that we're aiming to address there. I'd like to take this opportunity just to talk a little bit about Greenwich, my group at Greenwich, and how we're involved in the centre. And then DTM, Design Tools and Modelling. Okay, so I'm going to say DTM quite a lot in this presentation, but it means Design Tools and Modelling. Onto the cross-theme project, and what I think is very, very important is training. That's what really makes this a centre, is bringing together the folks here from devices, components, converters, drives, bringing them together, looking at training programs where people across these areas can see how design and modelling is undertaken in each of the other themes. Okay, this is where I'm from. Anyone been to Greenwich? It amazes me how many Brits have not been to Greenwich. Okay, we're on the River Thames. We're in London. We are. Everyone know what that blue line is? It's the 0 degrees meridian, and just outside this slide over there is the first pub in the Eastern world, because that's going east, okay? That's going east. Well, as you can see, back here is the University of Greenwich. And I'd like to think the University of Greenwich is the first university in the Western world. Now, my colleagues, there's some smart guys at Berkeley who said to me once, well, Chris, depends which way you're going. Now, you would be the last in the Western world if we were going back your way. Smart guy. Okay, so I run a group at Greenwich, very much based on EDA, tools, MCAD, modelling, simulation. Fairly big group. But our focus is very much in design tools, modelling, reliability, calculations of electronic products. We also engage quite a bit with professional organisations, and I think this is important with regards to the centre, and these are some of the activities that we have at Greenwich with the focus of our work. I do a lot of work with the IEEE, Components, Packaging and Manufacturing Technology Society. That's packaging, primarily. And the Reliability Society. There is an organisation called NAFEMS. Anyone heard of NAFEMS? Okay, you do a bit of modelling. Okay, now I saw a lot of modelling this morning, but NAFEMS puts out benchmarks for modelling tools to check. Just making sure when you're doing a modelling analysis, there's a number of benchmarks that you should check against first to ensure you fully understand the way a modelling tool is being used. We work, we're members of NMI, I saw someone from NMI this morning. Yep, okay. So we run a few events with NMI. Anyone heard of INEMI? Anyone heard of ITRS? International Technology Roadmap for Semiconductors. Well, INEMI publish a roadmap every 2 years on electronics manufacturing. Power electronics is going to have a whole chapter in the next INEMI roadmap. That's how important this is becoming. Okay, so there we are. You've heard from one of the cross themes this morning. John talks about structural, functional integration. Integration, big word. And I think it's going to be really important as we move forward in power electronics. You heard Barry talk a lot about integration as well. Okay, so design in power electronics. It is about, a lot of the systems we're going to be looking at in the future, smaller, lighter. We're going to be faced with higher power densities. We're looking for better efficiency. We want better reliability. We want to minimize EMI, EMC. Oh, and by the way, let's make it all cheaper. Okay? Many times a designer is faced with these sort of challenges, or some of these. That's a bit of a busy slide, but the point I'm trying to get across here is when you've got the power electronics design engineer, they're looking to optimize the design. They want to understand how variability could change in parameters. How does that affect my design? Parametric analysis. I've got tolerances. I need to understand tolerances. Sensitivity analysis. I want to understand electrical behavior. Circuit tools. I've got thermal issues becoming more and more important today. Electromagnetic behavior. And finally, stress and reliability. Anyone heard of DFX? Right. Big word in the design community. Design for excellence. Well, actually, we're looking for design for reliability, design for manufacture, design for test. But generally, you've got design approaches there and lots of modeling tool sets that you want to use to understand the physics. Another challenge for design is it tends to be very, very multidisciplinary. How many... It's going to be a silly question, this. How many electrical engineers in this room? Who's an electrical engineer? Okay, I'm not. Okay. I'm not. My background's applied maths. How many mechanical engineers? 1. 2. That's interesting. I thought there'd be more mechanical engineers. How many physicists? Semiconductor guys, yeah. Okay. Mathematicians, people from computer science or mathematical sciences. Oh dear, none. All right. EDA tools, that's where it all comes from, really. All the algorithms they're using there, the software that goes into EDA tools, a lot of computer science, a lot of mathematical science is feeding into that, as well as some engineers. Key thing here, within the center, and that's why it's a center. It's to bring across this expertise across the center. Design is very multidisciplinary, but no way can we ask someone to be an expert, a deep level expert in all these different disciplines. But you need to understand certain levels of expertise in those areas to be able to do good design. Again, another slightly busy slide, but this is, it's my take on, if you think of a converter, traditional design. We've got topology, a switching scheme. A designer might stay there with start with a white piece of paper and a filing cabinet back here. full of case history. Okay, now I've got a new design spec. So let's go through some of the key steps. Topology switching scheme. So electrical behavior, I could be using PSpice or something like this, all coming together, getting a good understanding of electrical behavior. Next thing is losses. So I need to think about some equations for losses. Then, how am I going to model temperature? And then, what a lot of people do is sort of assess reliability through tests. And now I'll build a product. Once I think I've got it right electrically and thermally, I'll go and do a lot of prototype testing. And then, finally, design assessment. Have my objectives been met? Efficiency, volume, weight. What about those constraints? Junction temperature, EMI. Do I really meet my reliability requirements? And then back. Redesign. If we don't meet that, or if we do, we hope we got it right, and we go to manufacture. Well, you don't need to do it with pen, paper, and case histories. There is a lot of digital technology there now, modeling tools, and you saw some of these in Barry's presentation where they've been pulling together and interfacing modeling tools. So we look at thermal and electromagnetics, we've got thermomechanical. Thermomechanical very much comes from the mechanical world. When it comes to packaging, probably one of the main codes there to look at stress analysis is ANSYS. We hear a lot today also about multi-physics. And I think Barry showed a plot before of COMSOL. Looked like a COMSOL calculation. And then, of course, we've got numerical optimization. We may be using these types of tools, finite element type tools, or circuit level tools, or system level analysis tools, or we use Excel, MATLAB, and things like that a great deal. So there's lots of tool sets there. We need to, where does design tools and modeling help us? We need to move away from this, where we do a bit of EDA, a bit of MCAD, not much of, just picking up on case histories, not a huge amount of actual analysis, probably because we don't understand the analysis tools, or we need better analysis tools to do what we want. But then we build prototypes and we do lots of this design iteration. Very expensive, very time consuming. This is where we really need to be. There are tool sets there today, but many times we struggle with a very high fidelity type finite element calculation that really to do a model, a multi-physics model of a whole converter is just too compute intensive. So where does the high fidelity finite element type calculations feed into a system level analysis type tool? And this is one of the big challenges. Just some examples. So design for reliability. We've heard a lot about reliability, and I think with regards to the centre, it's going to be very, very important to understand reliability in the future using what a lot of people call physics of failure type modelling tools and tests. This will be challenging because we're looking at new types of packaging technologies for integration in the future, but also new materials. So a lot going on today in interconnect materials, things like sintered silver structures. Do we really understand how they're going to behave? And can we model them and predict failure mechanisms and modes? When we build a model, we like to do a parametric analysis. Here, it's just looking at a wire bond. That's thermally cycling. A lot of good details coming out of this, but it's very much at a component level. But then, just changing some of these parameters, wire diameter there, we're looking at some of the mechanical behavior that's taking place, plastic strains in this case. And that has been checked, and people have tested for this, that does relate to a failure mechanism of a heel crack. All right, going through all these types of CAE type codes, technologies, there's a lot out there. Many of them come from different disciplines. You could spend hours going through all these types of different technologies. They are there. They have certain capabilities: thermal, thermomechanical, electromagnetic. There is a lot today in coupling, but at finite element type level. Many types of analysis we need to do quickly. We required a circuit, a system level type calculation where we can do quick calculations because we want to run this in an optimization type framework, like Monte Carlo type simulations, where you'll run many, many calculations within the design space that you're interested in. But why do all of this? Has anyone seen this type of plot before? Always the industry guys see this type of thing, right? It's, people say to me it's the valley of death. You get caught up in this. And really what this is saying is do everything you can as accurately as you can at design. Understand what can go wrong there. If you miss it, if you caught it at design, so let's say, we've built a power module, we've got a heat sink on this somewhere, it's got a certain heat sink dimensions. We think it's okay, seems to be okay with our case history, but actually we got it wrong. It should have been a bit bigger. Understanding that and correcting that at design, $1,000. You miss it there and it goes into prototyping, that mistake increases by a factor of 10. Into production and into the field. So the cost of getting design wrong can be huge. And you sometimes see headlines in the newspapers on this, like Toyota recently. They got something badly wrong in their design and hugely costly. Okay, a little bit about design tools and modeling in power electronics. Let me now move on to the cross-theme projects. And before I do that, this is kind of a summary of the activities going on in each of the themes and some of the tools that folks are using now. And just coming back to that slide that Barry showed in his presentation, where some of these tools, and one way of looking at doing design in power electronics is taking different tool sets and looking at how you transfer data from one tool set to another. So lots of activity in each of the themes. Some of these tools are cutting across the themes. But in a way, and maybe this represents industry, those sort of walls that I've put there is sometimes we get device guys, the silicon carbide guys, all looking at wafers and building those sort of structures, and they don't think much about packaging. And I'm not sure if this is that true today because we hear a lot about co-design, package device co-design, but maybe more in the microelectronics area. But essentially, you get it right in one area, you throw it over the wall, over the wall, over the wall. Design can eliminate that, where we're looking at cross-design and understanding of each of the areas in detail to do cross-design. And I think this is happening. It's starting to happen in companies. You look at guys that say at Philips, they sell a package today. They sell a package with a compact model that can then fit in a code like Flowtherm to do some system level analysis. So this is really looking at design across the themes. The DTM vision, if you look on the website, and we use this word co-design here, new methodologies, models and tools that provide an ability to undertake better co-design and faster co-design. And I'll come on to that in a moment. Co-design or co-simulation. So, this cross-theme project started in 2015, involves 4 universities, representing 3 of the themes: components, converters, and drives. So we're linking into those 3 themes, but this is looking at cross-theme activity. And the focus here is a 2-year project involving Bristol, Nottingham, Manchester, and ourselves at Greenwich, is to really look at some of these methodologies for fast-coupled behavioural models and physical models. Now, physical models tend to have geometry associated with them. They tend to know where on a board you are. Behavioural models don't have that sort of capability. So really it's how, with regards to different components like inductors, heat sinks, power semiconductors, what is the best representation in a system level analysis tool? And if it's a physical model, how can I solve it quickly? What type of techniques can I use to do that? Now, I had a number of, there's 4 work packages in this cross-theme project. The first one, which was looking at design flow and tools that are currently used in the community. And different types of model representation, which can be a simple analytical model. It can be a lump parameter type model, compact model, or your high fidelity type models, which is your finite element type analysis, or what's known as model order reduction. Anyone heard of model order reduction here? Okay. The whole idea of model order reduction, if you look at a code like Cadence, for example, they use model order reduction, but based on very linear type systems. Even ANSYS, being driven by the MEMS community, have model order reduction techniques, but again, mostly for linear type systems. What model order reduction allows us to do is take 100,000 equations that could be the basis of a CFD or a finite element calculation, and really eliminate many of those equations because they don't really affect the main result at the end of the day. All right, so it's taken a very big problem, scaling that down to a much smaller problem, but getting a reasonable level of accuracy in the final result. So that work package 0 is finished. There is a report that's available on that. Work package 1 is looking at different ways of representing components. And this is being led by Manchester. And this is underway now, so we've got the different components we're looking at here. And we're doing analysis and testing in how these components can be represented with regards to physical models and behavioral models. Remember, this is about coupling these in an effective way inside an optimization algorithm. Ourselves at Greenwich are looking at some of these model order reduction methods. This is building on some of the work that's been undertaken at Nottingham, who have been looking at thermal analysis with model order reduction techniques. We're going to look here very much at EM calculations and the non-linearities and how some of these techniques can handle that today. This is about undertaking fast analysis where you are looking at geometric effects within an optimization framework. Work package 3, system level modeling and design framework. So how to represent components either as physical models or behavioral models first. How do you represent them? Then model order reduction techniques and the optimization algorithms. So all of that fitting into a software framework. This is to ensure that we can do system level analysis, okay, in the most effective and accurate way possible using these techniques. Work package 4, demonstration and validation. So we are looking at a converter here that this will all be tested against with regards model accuracy. Deliverables. So the first deliverable is here. That's a report on design flow, tools and software specification. And we have a number of other deliverables here coming up for each work package. The final one involving software validation, software implementation. Also, what's very important in these cross-theme projects is follow-on projects. You know, one of the ideas here is certainly to identify where key challenges are that could be followed on with other projects. This project has its own focus, but many things come up as we go through the research here and we identify new challenges. This project is very much focused on electrothermal analysis. Being able to calculate stresses and damage and reliability in a system level type tool would be very interesting to see how that could come out of this. Okay, so that's the cross-theme project. I'd like to talk a little bit about training and outreach. Back in September, we ran the IEEE Thermonic conference at Greenwich. A number of folks from the centre attended that conference. This is probably for electronics, certainly packaging and going towards systems. This is probably Europe's biggest conference for thermal issues and thermal modelling. And we had a session at the conference there from the centre. The key thing here is engaging with the international community, folks who do a lot of thermal modelling around the world of electronic systems. We recently held a 2-day workshop on thermal modelling at Bristol. I wanted to run it at Greenwich, but Phil was insistent. It had to be at Bristol. But it went very, very well. Superb facilities there, and everyone had a great time. We had 30 attendees, all from the centre. And really, we're building a design community here. Folks who are doing a lot of design work and want to understand more about the techniques and the tool sets and build their skills up in this area of design. I'd like to thank also our friends from Mentor Graphics who were part of that workshop. John and Mike are sitting back there, and thank you for that. And also we had contributions from Motor Design Limited. So the format of the workshop was presentations, lectures on thermal modelling techniques, both lump parameter type models and then full CFD, finite element type models. And then most importantly, hands-on experience, using the tools, understanding the techniques, running real simulations. So that went very well. And I think as part of this centre, and this, I said before, this really what makes this a centre, is having this, these types of training sessions where you can start understanding how design and modelling is undertaken in each of these key themed areas and picking up best practice across this. And then looking together at new areas and new techniques. And that, think about it, integration, that word integration came out quite a lot this morning. And modelling and design is going to be very much part of that. Integrated power electronic systems and products. Going forward, and I've been speaking to Alistair. Where's Alistair? Is it right? Okay. So we've been talking about, I've worked a lot with power electronics companies. I think I know how they do design. I think I know where they bring different tools in and the sort of key design questions they have and the design approaches that they take. But Alistair said to me, do you really know? And I think there is an engagement to have here with industry which we'd like to take forward in working with industry in all of those four themes. How do you undertake design? And I think there's a lot we can learn there by undertaking a survey in bringing that forward. So we'll be working with the centre on that, but also Alistair at the MTC, and possibly with NMI, really, because I think this is a big area and we need to understand a lot more about. We see what's happening in universities, but really what's UK industry doing today? Training and workshops, needs to do more of these. We're engaging with the centre and looking at different areas that we can run workshops in the key areas of design tools and modelling. Okay, so I've forgotten what time's lunch. Okay. Well, this is my last slide, folks. So design tools and modelling, it's a key underpinning technology. It's a big area, it's a complicated area, it's very multidisciplinary, but it's going to be very important in the future with regards building power electronics components and systems. Strong theme here, co-design, co-simulation. We're always challenged with how much detail do I need in this model versus the speed I need to do my analysis and accuracy, particularly if I'm looking at parametric studies and optimization. That's one area that we are addressing and looking carefully at in the cross-theme projects. It was interesting the question we had at the end of the previous presentation, failure modes, failure mechanisms, do we understand them? And what is going on? Well, with regards physics of failure, reliability modelling, we're probably going to need new types of models or equations to capture that, particularly with some of the new materials we're looking at. And I've talked a lot about skills here, and I think that would be a big challenge and focus for the future. Okay, many thanks, folks.